This is the last video of chapter 13, and what we're going to talk about is Lagrange multipliers. Alright, so what is this about? Now remember we did that question, that was a question the web assigned, where you wanted to optimize a function of x, y, and z, three numbers, x, y, and z, whose sum is 56. Okay, so I want to optimize this function, find the maximum actually of that function under the constraint that x plus y plus z is equal to 56. Okay, so I can write it like this. Okay, so I have a constraint, the three numbers have to add up to 56, and I have a function I want to maximize under that constraint. So how we solved it before, well, that was easy in that case. That is, I have two equations, so I can solve for one variable, okay, and here we express z equals to 56 minus x minus y, and we put it back, this equation, into here, and therefore we only had an equation of x and y, and we can optimize this function of x and y the usual way, okay, that we saw. Now we're going to see something slightly different now, because sometimes the constraint is more complicated than just x plus y plus z, and so we're going to see the method of Lagrange multiplier, which is used to again maximize a function under a certain constraint. And those are very important in application, and let me just tell you one application. I won't enter into details. That's an very important example that is done in Math 4500, and that's relevant to those of you in BSFM. It's an example of portfolio optimization. Okay, and this is so what is a portfolio? Well, you have different stocks and you decide to allocate your money in different stocks. So the question is, would you want to allocate the money you have in the different stocks, okay, to minimize the risk of that portfolio and get a given return, okay? So that's the problem, one important problem in portfolio optimization. So here the constraint is the given return, so you want a given return. So how do you have to allocate your money to have a given return in order to minimize the risk of the fluctuations of the portfolio? Okay, and this kind of problem with that constraint leads to a beautiful object called the Markovits bullet. By the way, Markovits was an economist, and he actually won the Nobel Prize, and he was at Baruch College. Okay, so that's an example that is done in Math 4500 with the tools we're developing here. All right, so what's the point of, so how do you do these kind of problems? So let's illustrate it with an example. Okay, so let's say I have a function of two variables. By the way, the method works for any number of variables. So let's say I have a function of two variables, and I want to optimize it, so find the maxima and the minima under a given constraint. So here the constraint I want is that I'm only interested in the x and y, such that x squared divided by 9 plus y squared divided by 16 is equal to 1. Okay? So in other words, I only want to find the minima and minima and maxima of that function for x, y lying on this ellipse. Okay, so one way is exactly like we did for the product of the sum of numbers. That is, what I could do is solve the constraint for variables, say y. Here I will have plus y and minus y because of the square root, and then put it back in the function. So there I'm going to get two functions with plus square root and minus square root, and then optimize this function now, which is only a function of x. This becomes a one-dimensional problem, and that's calc 1. But this is slightly painful because of that square root. So can we actually do that right away? So let's look at how this looks like, geometrically. So the constraint, if you think about it, those are all the points, okay, are equals to such that lie on the ellipse. But if I look at it in 3 dimensions, right, so what point x, y, z satisfy that? Well, there are no constraint on z, so what that gives me is a cylinder, okay, so this is in the end all x, y, z, such that x squared 9 plus y squared 16 is equal to 1, okay? So that actually gives you a elliptic cylinder, okay? This is the constraint. Now, what does my function looks like? Well, that function of fxy for xy, this is a saddle, okay, or hyperbolic paraboloid, okay. So this looks like that. So now I want to optimize, right, this function, but under that constraint. So I want the xy that satisfy both. So I'm looking at the intersection of these two surfaces, okay? So this is how this looks like now. This is a static picture. In class, I'll show the more dynamic, what I can rotate. So this is my cylinder, and what we're interested in, okay, so is the intersection between both. So the xy that satisfy, xyz that satisfy this constraint, okay, so they're on the cylinder, but obviously I only want the value that are on the saddle, okay, so essentially this becomes a curve, okay, and so what we want is the extrema of fxy on that curve. So now geometrically, I can see that, well, my maximum will be where my saddle is up, right? And my minimum, let's put them in green, will be when my saddle is down. So I expect 2 minima and 2 maxima, okay? So this looks quite complicated, because if you look at the equation of the curve in x, y, z, it goes up and down, goes around. I could parameterize it, but it's slightly painful, okay? So, okay, this is just, all right. So here's a slightly better way using Lagrange multiplier. So here's the idea, right? So I have this constraint. So the constraint is, again, if I just look in the xy plane, it's no longer a cylinder, it's just the ellipse. So it's 9 plus y squared over 16 equals to 1. Okay, so I'm looking at all the points on the ellipse, okay? And now I will work with level lines of that function. So the level lines of this function, okay, they're like hyperbole but diagonal. So they approach like this, okay? Those are the level lines, okay? Now, here's the idea, is that if I look, so think of those level lines, say, as being very high, okay, like here, okay? Now, as the value approach, as I'm going down in levels, okay, I'm still not under constraint, but the largest value that satisfies the constraint will be right on one of the level line. It will just kiss it, okay, just touch it, okay? And same thing here, and also for the level lines going down. If they're too low, I don't intersect the constraint, I move slightly, and right when I'm at the minima, okay, is the first time that the level line touches the surface, okay? And so here's the thing. So first, if I look at the high level again, I go down, the maxima will be at the level line that just touches the constraints, okay? And that's the main idea. At the extrema, the level lines of both the function and of the constraints are tangent. And that's the key observation, okay? So right at the extrema of that saddle, of that function, on the constraint, the level lines of the saddle and the level lines of the constraint, the tangent, they're parallel, they're collinear, okay? Which means that if I think in terms of gradient, the gradient is always perpendicular, right, to the tangent. So that means if the tangent, if the constraint and the level lines of the functions are tangent, that means their gradients are collinear, okay? And that's the whole idea, okay? Now mathematically, so that's geometrically, mathematically, how does that translate? That means the gradient of f, where f is my function, is equal to a multiple, which I write lambda, so it's a parameter, it's a multiple called the Lagrange multiplier, is a multiple of the gradient of g, where g is the equation of the constraint. Okay? So that's the main idea that you have to remember. When I optimize a function under a constraint, the gradient of the function is in the same direction as the gradient of the constraint. And with that simple idea, we can solve the problem. Okay? Now let's go back to the problem. I'll go fast on the calculations because they're simple. The gradient of f is 4y, 4x. I look at this. The gradient of the constraint is just 2x over 9, 2y over 16. So that gives me two equations, okay? Because I know the gradient have to be collinear. So the x coordinates are multiple, and so are the y. So I get that 4y equals to lambda 2x over 9. That's one equation. The other equation is 4x equals to lambda 216 over y. And then you're just doing the algebra, trying to solve these two equations, okay? And I'm going to get, all right, so here I can simplify this one to say that lambda x equals to 18y. And here lambda y equals to 32x. I can eliminate the lambda and get the equation that x squared is equal to 916y squared. Okay? But that gives me, that's just a function of x and y. Okay? Which makes sense because I have here only used two equations, but now I have three unknowns. Not only x and y, but also this lambda parameter I introduced. Now I have to remember I have another equation, which is the constraint itself. Okay, we also know that the x and y must lie on the surface. So that x squared over 9 plus y squared over 16 equals to 1. Okay? And then you do the algebra. I'll skip over it, but you get that y equals to plus minus 2 squared over 2, and x is equal to plus minus 3 squared over 2. All right? Good. Okay? And then if you plug in, what's the maximum and the minimum of the function? If you look at 4xy, so you multiply these, the maximum will be positive, so it's when the two are plus or the two are minus, and I get plus 24. That's at the 2 points. Again, when the two coordinates are positive or they are both negative. And the minimum is at minus 24 where they have different signs. Okay? So this is consistent with the picture we had here. Always make sure that everything is consistent. That's true in this class, that's true in every class, that's true in every job. All right? So we have two maxima up and two minima down. Okay? So that's the idea of Lagrange multiplier. The gradients of the function and the gradient of the constraint are multiple of each other, and on top of that, I have the constraint equation that helps. Okay, so I have two equations, this one and this one. Now, if you want, you can combine the two in a single equation. It's called the Lagrangian. So you choose whatever you want. Usually the students like this one rather than consider the big function. So what is the Lagrangian? It's the function that you want to optimize minus lambda, the Lagrange multiplier, times the constraint. Okay? The two are equivalent. Why? Because if I optimize the Lagrangian here, so what do I want when I want to find the extrema? First thing I want to do is find the critical points. That means the gradient of that function is 0. So the gradient of that function has three derivatives. The derivative in lambda only appears here. That gives you this equation that gxy is equal to 0. That's what I did here. Then you also have the derivative in x and y. And if you think about it, this is going to give you actually the other equation that the gradient of f is equal to lambda gradient of g. Okay? Because when you take the derivative in x, you get the derivative in x of f minus lambda, the derivative in x of g. Same thing for y. Okay? So either you write it this way or you write it this way. Okay, let's go back to this example and solve it using the Lagrangian way. Okay, so we have this function. That's a function of x, y, and z, and I'm going to add a lambda to that. Okay, so either I write the Lagrangian, that is the function minus lambda to the constraint. Okay, the constraint takes this form. Or I write it and I find the critical points, or I skip one step and already write that the gradient of p, which is this function, is in the same direction as the gradient of g. Here it should be a gradient here. Okay. And the constraint equation. Those are the two equations you need. Okay. Okay, and then you just solve this equation. That's the algebra part. The calculus part is done. So the gradient of p is y squared z 2xyz xy squared, just taking the derivative in every coordinates of that. And then the gradient of g, so g is a linear function, so the gradient is always a constant. You get lambda to multiple 1, 1, 1. Okay. So now you have 4 equations, because you also have to include the equation of the constraint, 3 coordinate equation, and 1 constraint equation. And then that's the algebra part, so I'll go a bit faster. So you get these 3 equations. Okay, now you can solve the blue ones. Okay, so you can divide actually by y. So you equals the lambda, so these two have to be equal. That gives you this equation. That means that 2x is equal to y. The solution y equals to 0 is just dumped, because you want to look at product of integers. So it's going to maximum is going to be strictly positive. And then let's say you can equate this one and this one. Then you can again divide by y squared, so x is equal to z. So now I have these 2 equations put back in the 4th equation. Say that that is my constraint. I'm going to get x plus 2x plus x is equal to 56. So x is equal to 14, and then just unwind. Z is equal to 14 as well, and y is equal to 28. Okay. So again, the Lagrange multiplier method works for any function. So for a function of many, okay, it could be like 100 inputs. So here were the 3 inputs under a certain constraint. All right. So I think that's it. Thank you for listening.